Another approach that we've been pursuing for solar thermal power generation is in fact taking advantage of a new material that we've developed that are called optically transparent thermally insulating aerogels. The idea here is to create a new type of receiver design instead of typically what you see out in the field, which is say a parabolic trough type system that relies on a vacuum tube that has an absorber surface on it, and that mitigates the losses. The idea here with this optically transparent thermally insulating aerogel type receiver design is that in fact you use that as a great insulator that allows us to also optically transmit all of the sunlight onto the receiver, which is the absorber coating. And because you have this aerogel, basically you can minimize and suppress the radiative losses because you're internally keeping the pipe, for example, very hot with a non-selective surface, so it could just be a black absorbing surface. And then you minimize emissive losses because the rest of the outside is cold. So in this way, you can basically not use you don't have to use vacuum. You don't, like I said, don't have to use a selective surface. And then you can create a receiver design that's much simpler, potentially low cost, and utilized into these solar thermal power plants. This approach is in collaboration with Gong Chen's group at MIT, where in fact we've been starting to now not only synthesize these really neat materials, these optically transparent thermally insulating aerogels, but also creating a prototype at kind of creating a field with concentrating optics and then beaming this sunlight onto this aerogel-based receiver to show the kind of significance or the opportunities with this different type of absorber system. There are certainly many plants that exist already in various parts of the world. For example, in Spain, they already have a deployed plant. They have a plant, I believe, in Arizona as well. So there are various plants. Right now, the cost is still significant, and so that's why you don't see it readily available everywhere. And often they're subsidized by various government programs. And so I think to really get us to the next step is improving the performance, essentially the efficiency of these systems, such that they make it economically viable to have them deployed more readily everywhere. I would say that with these solar thermal aerogel-based receiver designs, this gets us potentially closer. The concentrations that we need, because of the fact that we're insulating very well the receiver, mitigates the need for really high concentrations. And the mirrors in these types of systems are typically one of the key economic bottlenecks. And so we think that we can get kind of the price down per kilowatt hour, right, which is a really critical metric that allows us to then be able to start to think about deployment more broadly of these solar thermal power systems. Yeah, so the commercial viability is all dependent on the ability to scale up these materials. So right now we've demonstrated, like I said, in more of a prototype demonstration phase, which is about 1 meter squared or so of aerogel, that we can in fact create an efficient receiver design. However, this is in a lab, and the key here is to be able to then take it to the next level where we can really create a lot of this type of aerogel in a very mass-produced manner. And this is something that we will have to work with industries that develop aerogels already. The key to our work is, like I said, the optical transparency of these aerogels. Aerogels are known to have very good thermal insulating properties. The problem is typically they're not that optically transparent, especially they have this kind of bluish tinge to them because of the scattering involved with these materials. And so what we've been able to do is be able to control much more readily the pore sizes of these aerogels, as well as the size of the pores, such that we can mitigate the scattering in this bluish, in having this bluish type tinge to it.